Welcome back to Calculus 2, Section 7.4, Area and Arc Length in Polar Coordinates. In the previous video, we did polar coordinates. This time we're going to do a little calculus in polar coordinates. We're going to start with area enclosed by a polar curve. We saw last time that there's a particular curve called a limacon. When the ratio of the A and the B are equal to 1, you get a cardioid. Here we're looking at a cardioid given in terms of cosine. To trace out this entire cardioid, we need the parameter theta to do a full revolution, 0 to 2 pi. We want to consider how much area is inside of this closed curve. Let's start off by noticing that this ray line segment starts at theta equaling 0, and let's have it finish at theta equal pi over 2. In doing so, that line segment traced out area, capital A. Let's think about how we can do calculus to compute that area. We started the semester, this course Calculus 2, with considering area under a curve. This is area enclosed by a polar curve. We're going to do the same notion. We're going to partition our area into segments. At the beginning of the course, we used rectangles. Here we're using slices determined by different values for theta, A1 through A5. Those slices produce points on the curve, here given in bluish purple dots. And note that if we add up A1 through A5, that we recover the true area. That reduces our problem to estimating each one of these AIs. To keep track of things, let's note that these dots on the curve correspond with different theta values from 0 out to pi over 2. That we're in the situation where our theta is running from some alpha up to beta. For us, in this particular instance, 0 up to pi over 2. Just like before, we can consider a change in that variable, denoted by delta theta, which goes from the ending value minus the beginning value over the number of partitions we desire to make. And that these points correspond with inputs, theta I, found by adding to the beginning value I copies of delta theta. So very similar to what we did at the beginning of the course. To produce estimates, what we'll do is we'll look at these shaded regions, which are sectors. And there's a very simple formula for a sector: 1/2 the radius times the angle. For our angle, we're going to have delta theta as the angle. And then for the radius, we have the function output as the radius. So for example, for S1, if we plug that in, S1 would be given by 1/2 the radius squared times the angle. And then we have a similar formula for each of these 5 sectors. Adding up the 5 sectors gives an approximation to the true area. Note, because there's a little bit left over that we're not accounting for. So it's only an approximation, but as before, if we take the number of partitions to be larger and larger and larger, we get better and better approximations. Let's see that happen. All that we've done here is we have changed the notation from SIs to 1/2 radius squared, where the radius is given by f at theta and taking theta I. All right, let's watch a little movie here. We had beginning with n equaling 5. This movie will go out to representing n equaling 100. And already the picture is looking quite nice, in that the sectors produce a very good, when we sum them together, produce a very good approximation of the true area. And thus, by taking a limit as n goes to infinity, This quantity on the right, taking the limit of it, will yield a definition. It's a Riemann sum, a definite integral from theta equaling alpha up to theta equaling beta with integrand f, the function f, quantity squared. I like to bring the 1/2 out to the front, so I've done that. And then the delta theta in the limit turns into the differential d theta. Nice. Note that this formula works very nicely when we have theta beginning at some value alpha and finishing at beta, where beta can be no bigger than the initial value plus a revolution 2 pi. Nice. Doing an example, supposing we want to find the area enclosed by the rose curve, r equals cosine 2 theta. So a rose curve has a picture which looks like a flower. In this particular case, since the parameter that we pass into cosine is twice the parameter theta, we end up doubling the 2 to get 4 petals. In other words, if this was cosine of an even 4 theta, we would get 8 petals. But if it was cosine of an odd 3 theta, for example, we'd have 3 petals. Now we want to find the total shaded area. But these petals, by symmetry, all have the same area. And again, by symmetry, we can consider just half of a petal. So that if we take half of a petal, its area, double it, we get the area of a full petal. And then times that by 4, so we need 8 copies of this blue shaded area. This blue shaded area corresponds with theta values beginning at 0. And then if we open up theta, for example, if we take it out to theta equaling pi over 6, let theta equal pi over 6. Cosine of 2 times pi over 6, that's cosine of pi over 3, is 1/2, and indeed that point occurs on the circle of radius 1/2. Then where will it return to? Where would this point return to the pole? Well, that's going to occur when cosine is 0. Cosine of pi over 2 is 0. 2 times theta equaling pi over 2 means that theta is pi over 4. Theta is pi over 4. Nice. We have our alpha and beta. And then r is our f of theta. So we plug that into the formula. As noted earlier, that what we're going to compute, A1, is 1/8 of the total area. So to get the total area, we multiply A1 by 8. And as we just saw, the alpha value is 0, the beta value is pi over 4, and everything else is just following the formula. All right. The integrand is cosine squared. We have a way to deal with that. We can use a half-angle identity. And we can change from a power of 2 to a power of 1 at the cost of doubling the parameter to cosine. And multiplying this out, we come up with a nice quantity. Sine of pi is 0, and that term will go away. And thus we have A equaling pi over 2 square units. Very nice. Here's one for you to try. This rose curve, as mentioned, will have 3 petals. Find the total area of all 3 petals. That was area of a region bounded by a polar curve. Let's do the area between 2 curves. Here's a nice example which does not require calculus. If we want to find the area within r equal 2, the red circle, but outside of r equal 1, the blue circle, we can use a simple formula to calculate the area contained in the red circle minus the area contained in the blue circle. Very simple, big minus small. In doing so, pi 2 squared minus pi 1 squared. 4 minus 1, 3 pi is the area within the red circle, but outside of the blue circle. Let's do something that involves calculus, but really comes back to the same principle. And note that the setup is the same. Area within, but outside of another curve. So again, within the red curve, but outside of the blue curve. So we need a little bit of calculus here, but again, the notion is going to be the same principle, big minus small. Well, if we're going to do that calculus, we're going to set up an integral. We need an alpha and a beta. Let's start by thinking about where these two curves intersect. So if you want the red curve to match the blue curve, then you want 2 sine theta to equal 1. Then you can solve for sine of theta and find that theta must be pi over 6. That's the starting point. Let's watch 2 dots traverse their separate curves. And then I'm stopping here at pi over 2 because we're going to be able to take advantage of symmetry. That gives us a beta value to work with. Alpha pi over 6, beta pi over 2. And then I've shaded the region that we want to find. But what we're going to do is we're going to consider the area enclosed by the blue curve. So that'd be from the blue curve to the pole. That'd be the small area. And then subtract that away from the area inside of the red curve all the way down to the pole, from this alpha to that beta. So set that up as the big area and the small area. This is for the red curve. The red curve was r equals 2 sine theta, alpha to beta. And then the small curve, the blue curve, has radius constant 1. A2 is simple to compute. So go ahead and do that. A1, we use that same trick of changing from a power 2 down to a power of 1 at the cost of doubling the input parameter. And then evaluating A1. And again, the notion was that we want to take A1 minus A2. So pi over 3 minus pi over 6 is going to give us pi over 6. But remember, this is only half of the desired area. And so we need to double that quantity. Pi over 3 minus pi over 6 gives us pi over 6. And then plus rad 3 over 4 doubled up produces the area that is described. All right. The key thing is that we have big minus small. Here's one for you to try. Area within, but outside of the other. And then reusing the previous example, note that here the setup is a little bit different. Find the area common. So you want area which is shaded both red and blue, which would be this area here. And the way that you're going to want to do it, or one way to do it, is to think of an A1 and A2, but this time instead of a difference, you're going to add. So what you should find is that you're going to integrate once from 0 to pi over 6 using the red curve, and then again from pi over 6 to pi over 2 using the blue curve, and then add those values. Nice. So that's area between two curves. Another application that we can consider is how long is the curve? Arc length. Well, we've studied this notion already. The only difference is that we want to use a curve which is a polar curve. So if you look at the curve and you describe the curve as r equal f of theta, then you can come up with parametric equations in the xy plane. Since x is equal to r cosine theta, you use that polar conversion and come up with x equals r written out as f of theta, cosine theta, y equals r written as f of theta times sine theta. And then you just repeat everything that we've already done. We're going to need a derivative of x, a derivative of y. This is a derivative in theta. Because it's a product of two functions in theta, we need the product rule. Let the derivative fall on f. Then let the derivative fall on cosine, get negative sine. Same story for the y, let the derivative fall on f, and then let the derivative fall on sine to produce cosine. Thinking of the formula, we're going to need a sum of squares. We're going to have to square each of these derivatives. You have the simple formula for the square of a binomial, 1 which is a difference, and then 1 which is a sum. We're going to want to add these two quantities. These middle terms will cancel away. And on the ends, the f prime quantity squared is common to these first two terms. So by the Pythagorean theorem, the cosine and sine factors will go away, go to 1. Same thing on the f of theta quantity squared. Bringing that together, all that we're going to have is f prime quantity squared summed with f quantity squared. F quantity squared is the same thing as r quantity squared. And if f is r, then f prime is dr d theta. Nice. So with this, we're able to plug into the arc length formula that we've studied before. Our curve is going to be defined for thetas coming from alpha to beta. So we swap out a to b with alpha to beta. And then x prime squared plus y prime squared, we saw, takes the form r squared plus dr d theta quantity squared. Plugging that in, changing the differential from dt to d theta, we are done. That's the formula. Great. Let's apply the formula in an example. Suppose that we have a cardioid, 1 plus cosine theta. Then we look at the formula. To make this cardioid, we know we want an alpha starting at 0, going out to beta 2 pi. The r value is 1 plus cosine theta. We're going to need to square that. A derivative of r is going to be 0 minus sine theta. You can simply write down minus sine theta. Squaring that quantity, multiplying out, looking at the radicand, the binomial squared is going to produce 3 terms. And then the minus will go away, giving us sine squared. Once again, Pythagorean identity, 1 plus 1 is 2. And then here we're going to be able to take advantage of factoring off a 2 from the 2 terms in the radicand. And recalling the half-angle identity, can come up with 1 plus cosine theta is twice cosine squared of some input. 2 times 2 gives us 4. And here we have to be a little bit careful in that cosine squared is a non-negative value, but when we take the radical of cosine, we cannot simply write down cosine. We need to write down the absolute value, as cosine may take negative values. To remove the absolute values, what we can do is we can consider the bounds of integration. Cosine begins at a value of 1, goes to a value of 0, and then becomes negative. It takes a value of 0 at pi over 2. So if we let theta go up to pi over 2, as much as pi over 2, then we know that cosine of theta over 2 will be non-negative. And then by symmetry, we can do that so that the constant out in front gets doubled from 2 to 4. Nice. So note that here we have an integrand which no longer has the absolute values. The way that we did that was by adjusting the bounds and using symmetry. Excellent. So evaluating that, we come up with an arc length of 8 for the cardioid 1 plus cosine theta. Fantastic. Here are some for you to play with, which is just a variation on the example that we did. And that is the end of the video. Thank you so much for watching. See you on the next one.